Alright gang, here we go. So this is the series of videos on high school physics. I record this for high school physics course at Spring Hill High School. If you're joining us from elsewhere, welcome. We're going to start right at the beginning, the Science of Physics, Unit 1, Chapter 1. This is it, guys. Here we go. Alright. So what is physics? So we've talked about this a little bit already, but physics is really concerned with trying to answer the big why questions. Okay, so we're trying to answer why are there rainbows? Why do objects fall? How does our sun produce energy and stuff like that? And so big and small, how does gravity work? Those are all physics ideas. Okay. In class, we talked about what topics you expect to cover in physics, everyday examples, how your effective physics. We talked about all that in class. So areas within physics, these are the main ones that are listed in our textbook. We're going to cover this stuff in semester 1. All right, we're going to talk about mechanics, motion, falling objects, friction, weight, spinning objects. We'll talk about planetary motion, so circular motion, so on and so forth. We'll touch on thermodynamics a little bit, talk about melting and freezing, and how engines operate, so on and so forth. And then in semester 2, we're going to mostly focus on these guys here. Focus on vibration and waves. So sound waves, we'll talk about pendulums and springs, so on and so forth. And then we'll talk about light, mirrors, and lenses, the energy of waves, and that brings us directly into electromagnetism, meaning we'll talk about electricity and magnetism and light, electrical charge, and you'll learn how to read circuit diagrams. It's going to be a whole lot of fun, all right? We probably won't have time to touch on relativity or quantum mechanics in this course. All right, so physicists, it's fascinating is the history of physics. Okay, the idea of using the scientific method to solve problems is actually pretty new in the grand scheme of human development. Okay, so this guy, you've probably heard of him before. There's this guy named Aristotle. Yeah. He said that, well, heavy objects are going to fall faster than light objects. And that was kind of like the general idea that most people operated with. Number one, because most people didn't really have a reason to not think that. It's just kind of like, well, where are we going to get food? Okay. But Aristotle was a smart guy, so they just assumed he was right. And then Galileo came along, and he was all for throwing things out of whack. He's the guy that really put his foot down and said, yeah, we do orbit the sun. Copernicus was correct. And so Galileo went in with this hypothesis, but he thought something was fishy was going on. So he decided to, if he could develop a thought experiment or like a situation, he could prove once and for all that this idea was wrong. All right. So he considered this idea: if you take one heavy object and then one light object, in this little picture here, we've got bricks. Okay. So we've got a heavy brick and a light brick, and we drop them. Right. According to Aristotle's theory, and the prevailing theory of the time, was that the heavy brick would fall faster. Right? So you drop them at the same time, the heavy brick would hit the ground first, and then the light brick would hit the ground. Now then he thought to himself, well, what if we took these two bricks and we tied them together? All right? So if we tied them together, right, and we made these guys attached to one another, then logic would dictate that that what would happen is this large brick would start to fall. Right? This guy would start to fall and would make this string that was connecting them super tight. right? Because the large brick's falling faster. Imagine yourself pulling a rope. You're pulling a wagon with a rope. You start moving. The wagon's not moving. The wagon won't start rolling until the rope gets tight and you start putting tension on it, right? So that's the idea. Like the large brick's going to start falling, and then it'll eventually make the string tight, and then the small brick will start moving. And then once the small brick starts moving, because it's being dragged faster than it wants to by the large brick, then the small brick is going to create a drag, right, and start pulling this way against the large brick, all right? So you could imagine that happening. Like, just imagine pulling a wagon. You're pulling the wagon pulls back on you, okay? That's kind of a generally accepted idea and seems very reasonable given their original hypothesis, that large objects fall faster, all right? Then he said, well, that's all well and good, but really, if we connect these two by a string and the string gets taut, doesn't this whole thing just become one giant brick that's really the mass of the small brick plus the mass of the second brick? And so that was his general idea. He said, well, if it's all one object, that means the whole thing is heavier. So therefore, that more heavy object set should fall faster than the original. And that's kind of what these arrows down here. So a large object falls this fast. This is the representation. And then once you've tied them together, there it's going to fall slower. But at the same time, it should also fall faster. So the idea was, well, he's developed a contradiction. All right. So since these two bricks can't fall faster than they were before and also can't fall slower. They can't do both. It's not possible to go faster and slower at the same time. You can conclusively say that the original hypothesis was wrong. All right? So that's the general idea of how thinking in physics has evolved, is we come up with a hypothesis and then you try to come up with situations that prove it wrong. Okay? In class, we talked about the think tube. Remember, that was the tube that had these guys, and then there were the beads. You had a red bead, and I think it was a green bead, and then there was the blue bead, and then the yellow bead over here. Remember, we talked about how we could, determine how the strings were connected by using the scientific method, so on and so forth. All right, so let's move on to measurement. All right, so measurement, we do this in physics all the time. I mean, it's a science class, so we got to make some measurements. Okay, dimension is the physical quantity that you're being measured, right? So if the dimension is the length or the mass, time, volume, whatever it is you're measuring, we also call it the dimension, all right? It's a science class, so we're going to use SI units. Remember, it's SI means Système d'International. It's French. Ooh, so fancy. All right? And these all should be very familiar for you now that you're in physics. Okay, you got your meters, your kilograms, second, liters. Okay, there's several others that are like the SI base units. Okay, we also have a bunch of derived units. Now remember, derived, that's from the math term where you derive equations, so on and so forth. Okay, so derived units are units that are a combination of the original base units Okay, so for example, the Newton is the SI unit for force. Okay, it's like how much it's the measurement of how hard you're pushing on something, more or less. All right, and so the Newton is a derived unit, and it's equal to kilogram times a meter per second squared. All right, and we'll derive that later in class. But that's an example of a derived unit. So a derived unit is a unit for something that's a combination of our other smaller individual units like meters, kilograms, seconds, liters, etc. All right, prefixes. This is we use the metric system, so we got all these prefixes. Remember, they're always in powers of 10. All right. So here's a list of our prefixes. This is given in the book. This is in your note packet. The equation sheet that we let you use for quizzes and exams also has more or less the same thing set up exactly the same. So you got your powers, all right, here. So this means 10 to the minus 18th. So there's 10 to the minus 18th meters in 1 attometer. Okay, those are ridiculously small. And then, like a centimeter, there's 10 to the minus second centimeters in 1 meter, or you can read them backwards and you can say there's 100 centimeters in 1 meter. Once you get to the positive powers, it goes the opposite direction. So at the kilometer, that means that there's 1,000 meters in 1 kilometer, or there's 0.001 kilometers for every 1 meter. All right, you can kind of work it that way. Regardless how you want to think about it, you do have to be able to convert between all these different units of metric system. All right, so let's do a couple together. So we're going to convert 22 kilometers into centimeters. So we got to go from kilometers to centimeters. Now, you can do this in one step. It's not hard to do, but we're just going to do it in 2 steps just to keep everything, keep it simple. All right, so we're going to take kilometers and we're going to take it into meters, and then we're going to go to centimeters. I suggest, until you get used to doing these, always just go back to the base unit, and then you don't have to worry about it. All right, and then you don't have to worry about being confused. So we got 22 kilometers. All right, and we're going to get it into centimeters. Now first we're going to go to meters. So we're going to do a little bit of dimensional analysis. We're going to set up our parentheses. We'll put kilometers down here in the bottom. We'll put meters up here in the top. Now here's what I want you to do. You got to think to yourself, based on this thing, the first step you're going to do is you're going to say, all right, which of these 2 things is not my base unit? Which one of those is the one that I don't start with? The meter is the base unit, kilometer is not, so we're going to put a 1 with the kilometer. Then we're going to look over here, we're going to find kilo. Alright, kilo's right here, and remember there's 10 to the 3rd meters per kilometer, so we're going to remember that 10 to the 3rd, and we're going to throw that guy in right here. So we'll put 10 to the 3rd in there. Alright, and then we're going to do the same thing, but we're going to do it for centimeters. Now we start at meters. Remember, our kilometers cancel here, and then we got our meters. So we're going to put our meters down here, and then centimeters up top. All right, which one's not our base unit? Well, centimeters is, so we'll put a 1 right there with centimeters. And then our meters here, well, we can go back, find centimeters. It's right here, okay? And for every 1 centimeter is 10 to the minus second meters. So we'll take that 10 to the minus second and we'll throw it in right here. All right. Now we can do a little bit of math. You might be tempted to grab your calculator, and that's totally legitimate. But you can also do this math. The metric system and scientific notation makes this math super easy. You got 22 times 10 to the 3rd over 10 to the minus second, right? So remember, when you take exponents, and if you take an exponent and you divide them, right, you know that essentially these get subtracted. So really this becomes 10 to the 3rd minus a negative 2. Right? So this becomes 10 to the 5th. So anyway, so this becomes 22 times 10 to the 5th centimeters. Or if we wanted to be super fancy and convert it to scientific notation, it would be 2.2 times 10 to the 6th centimeters. All right. Let's try another one. A typical bacterium has a mass of about 2.0 femtograms or femtograms. Express this measurement in terms of grams and kilograms. So we got 2 things. We got to convert it to grams, and then we also got to convert it to kilograms. So we're going to start with 2.0 FGs. All right. We're going to put FG in the bottom, grams in the top. Grams is our base unit, so we're going to put a 1 with the FG. Find femto, 10 to the minus 15th. 10 to the minus 15th, don't forget it. We'll write it in here, 10 to the minus 15th. All right, do that math. Well, this is easy. So 2.0 times 10 to the minus 15th grams. All right, so that's the first part. That's the number of grams. Now we got to convert this to kilograms. All right, so we got our grams here. We're going to put our grams in the bottom, our kilograms in the top, put our 1 with the thing that's not the base unit. Remember, the grams is our base unit. All right, so we go back, we find kilo. It's right here, 10 to the 3rd. So we'll put 10 to the 3rd with this guy. All right, and then we just do a little bit of magic math. So 2.0 times 10 to the minus 15th divided by 10 to the 3rd. Well, these exponents, remember, they're divided, so they subtract. So 10 to the minus 15th minus 3, so it becomes 2.0 times 10 to the minus 18th kilograms. Pretty slick. All right. I think there's one more. If a woman has a mass of 60 million milligrams, what is her mass in grams and in kilograms? So this is essentially the same thing, only we're starting in milligrams instead of femtograms. One thing I suggest, if you see a number like this, and there's like a bazillion zeros after this thing, convert it into scientific notation. It'll make your life easier, promise. Alright, so we're going to move the decimal place from here to here. Okay, so it goes 1, 2, 3, 4, 5, 6, 7 places. So this becomes 6 times 10 to the 7th milligrams. Alright, so that's what we're going to start with. 6 times 10 to the 7th milligrams. Alright, first step is we need to take it to grams. Alright, so we'll put milligrams in the bottom because that's what we're coming from. We'll put grams in the top because that's what we're going to. Milligrams is our non-standard unit. Milli is right here. It's 10 to the minus third. So we'll throw 10 to the minus third right there. Alright, and then that's it. So 10 to the 7th times 10 to the minus third. Remember, when you multiply exponents, you really just add them. So 7 plus a negative 3 is a 4, right? So we get 6 times 10 to the 4th grams. All right, now do the same thing but with kilograms. So we put our parentheses right here. We got to go to kilograms, so we're going to put grams in the bottom, kilograms in the top. 1 goes with kilograms, and we've done kilograms several times now, so that's 10 to the 3rd. They're dividing, so they subtract, so it becomes 6 times 10 to the 1st kilograms, or essentially 60 kilograms. Pretty slick, huh? Let's keep moving. So accuracy and precision. So precision is the degree of exactness for a measurement. Okay, so you're trying to see how precise your values are. So you want to know how close to each measurement is. So precision is the degree of exactness. So if you stick a mass on the scale and every time it gives you the same value, you know that your device is pretty precise. Accuracy is how close it is to the correct value. Okay, so if you put a mass on a scale, say you have an exact mass that's 20 grams, 20.000 grams, you stick it on your scale and it tells you it's 18.000 grams, you know it's not very accurate because it's giving you the wrong answer every time. Okay, but if it tells you 18.00 grams every time, then it's very precise, even though it's not accurate. So this is a good way to kind of visualize it with these targets. This is pretty standard here. So it's accurate and precise. Look, we got a target. You got 4 dots. They're all on the bullseye. The bullseye is what you want to hit. Okay, so therefore it's accurate. All right. It's also precise because all 4 dots are pretty dang close together. And the second one, we're not accurate because we totally missed the bullseye. But all 4 dots, or all 4 holes, are really close to one another. So it's actually pretty precise. Then we have accurate and not precise. So we've got 4 bullet holes. Okay, we're not accurate because we're not really very close. Or I guess you could say we're kind of accurate because it's close to the bullseye here. Okay, but we're not precise because they're kind of all spread out. This one's to the bottom left, top right, bottom right. Okay. And then the last one here, we're not accurate and not precise. We're not really close to the bullseye. Our middle is kind of like right here-ish. Oops. Our middle is kind of right here-ish. And they're kind of spread out. So we're not accurate or precise. Finally, we've got Sig Figs going on. This is a pretty funny comic over here that we decided to include. And then so we've got our 3 rules of Sig Figs. All right. So non-zero numbers always count as significant figures. So non-zero, so we're talking about 1 through 9. Okay? Anytime you have a 1 through 9 number, then it is a significant figure. So this guy here, 14579, 1457, this has 4 Sig Figs. All right? Now zeros, okay, they're different beasts. This is what starts confusing people. There's 3 individual rules for zeros that you kind of have to watch out for. All right. The first rule is anytime you have leading zeros, so zeros in front of the number, they never count. Alright, so all of these zeros, because they came before the 0.0025, they are not significant. So this number here has 2 sig figs. Alright. Sandwich zeros are zeros that occur between two numbers. They always count. Okay, so those are sandwich zeros. So this number here, because those zeros are before or after a 1 and before the 8, they're sandwiched, so they are significant. So this guy has 4 sig figs. And finally, trailing zeros. Now this is the rule that throws people off. They only count if the number has a written-in decimal point. Alright? So this number here, 100, there is no decimal point right there. So therefore, this guy has 1 sig fig. Alright, they're trailing zeros, but there's no decimal point, so it has 1 sig fig. This guy here has the decimal point is written in, so those zeros do count, so it has 3 sig figs. Alright, and this guy here has zeros after numbers, but there is a decimal point, so it does count, so it has 4 sig figs. Alright, those are your zero rules. And in class, and on Google Classroom, I've posted a pretty handy, I think it's pretty nice, Sig Fig handout to help you out. Finally, we've got exact numbers, right? Exact numbers are special because they have unlimited sig figs. And this really only matters when you're doing your calculations and trying to keep track of how many sig figs your answer should have, all right? So they're determined, there's two ways. They're either determined by definition. So, for example, it's defined that 1 inch is 2.54 centimeters, right? So any sort of like exact conversion like that, so like there's 12 inches in 1 foot, there's 5,280 feet in a mile, etc. All those are defined conversions, so they are exact numbers and they have unlimited sig figs. All right. The other way is if they're counted. All right. You have 3 apples. That's like saying you've counted 1, 2, 3 apples. So if you're going to write this number down, you'd say 3.000000, and where would you stop? You'd never stop, right? Because there's exactly 3. So you say there's unlimited sig figs for counted numbers as well. All right. Sig Fig Calculations. So addition or subtraction here. I'm going to drag myself over here, see if that helps get us out of the way. All right. So that's how you find how many sig figs there are. Then you have to be able to do the math with the sig figs. All right. So addition and subtraction rule. Put them in columns. All right. And then the final answer, you're going to round the final answer to the first column from the left containing an estimated digit. All right, now that's confusing, so let's do this real quick. So we've got 97.3. I'm going to do this up here. 97.3 plus 5.85. Now remember in 3rd grade, whenever you learn this, that you were taught to line up the decimal points, right? So you're going to line up the decimal points with each other. Okay, and then all you have to do is you're going to add all this guy up. So you're going to say 97.3, so we got a 5, we got a 1, we got our decimal point. Yeah, that's a 1. And then we got a 1 up here, that's a 3, and then a 1, and then that's a 10. Right? 103.15. That's confusing. Let me erase some of these little lines I've written on here. Oh, dang it. Alright, let's see. Alright, let's start over again. So we got 97.3 and plus 5.85. Okay, so we're going to add all that up. So 103.15. Okay. Yeah. Alright, so all that adds up. Now, this number here, this is our estimated digit for this value. Okay, so that is where our number has to stop. So we're going to round this based on this spot, so we have to look here. That number is 5 or above, so our real answer, considering sig figs, is 103.2. Alright? Multiplication is way easier. All you have to do is count how many sig figs it has, each of the digits you multiply or divide, and then your answer has to have the same amount as the smallest amount of sig figs. So this number here has 3 sig figs because they're all non-zeros, and this number here has 3 sig figs because they're all non-zeros. So therefore your answer has to have 3 sig figs. So we would just take 123 times 5.35, and we get 658.05. Alright, 658.05. Now let's think here. We've got 3 sig figs here, 3 sig figs here. My answer can only have 3 sig figs. So I'm going to start at the left, start counting. So I got 1, 2, 3. So I have to round here. Okay, so I'm going to look at the 0. Well, the 0 is less than 5. So I don't round up. So it just becomes 658. Alright. Here's some more practice for you that you can try on your own. And so these are all correct given the number of sig figs that you need to have. Let me know if you have any questions. Do some of those practice problems, and I'll see you on the flip side.